We are now ready to learn expectations. And we learned the abstract theory of integration, the so-called Lebesgue integration theory, on this abstract space. And it's time to go back to probability theory. So how do we do that movement? We replace the set by omega, the abstract sigma algebra S by abstract sigma algebra F. And then we assume that mu is a probability measure, and then we use the letter P for probability in this case. So what has changed now from the general setting? Only one tiny thing. The one tiny thing is that this measure is now a probability, which means it is a measure with mass 1. Nothing else has changed. But we delete this notation, and this is where we are now. The expectation is defined actually just as an integral. So expectation of a random variable x. We now assume that x is a random variable, which means that it's a measurable function from omega to the real line. From the Borel preimages to the abstract sigma algebra F. Is this measurability? And then we want to calculate or define what should be the expectation of x. And there are actually two cases. So assume first that x is non-negative, so then we define it as, well, we define it just as the Lebesgue integral with respect to this measure, and the integration space is omega. And this definition is well done if x happens to be non-negative and measurable function. So from the previous part, we used this plus to denote non-negative functions and m for measurable functions. And in the same way, we can define if x is a signed random variable, which can take positive and negative values. So, well, we define the same way for x being now we require it to be integrable with respect to the probability measure. And the key thing here is that in this definition, we allow the integral or the expectation to have infinite values. In this case, we allow it to be not infinite, not minus infinite, but positive or negative real number or 0. Is there anything else that we need to look here? We might also note that what would L1 now mean? It would mean those random variables for which the expectation of the absolute value of x is finite. You see how convenient this writing becomes when we don't need to write this integral sign anymore. We just write E for expectation, and that's it. That's the definition. Do you have questions? Then I might actually declare that whatever we learned so far, monotonicity, linearity, this is just a change of notation. So all of the theory about monotonicity and linearity and so on works in this case as well. And all the definitions are hidden inside under the hood here. So for the non-negative thing, we know that we approximate x by simple random variables. So finite range random variables from below and take the supremum. And that's how we get this expectation. Maybe one example could be in place. Let's calculate one expectation for one concrete case. Assume that omega is the set of 0 and 1. Let's take, when we have a finite omega, so then in that case, we usually take the power set as the sigma algebra, where we can make integrals. And then let's say, what should be a probability measure? Let's take a probability measure. Let's define it this way. It's 1 minus p times the Dirac measure at 0 plus p times the Dirac measure at 1. And let's take, what is a nice p? Let's say, let's take p to be equal to 1 over 37. Maybe you know why 37 is a nice number here. Okay. And let's see what this Dirac measure notation means. Just to emphasize that if we want to calculate the probability of some set A, so then we say it's 1 minus p times Dirac measure at 0 of A plus p times the Dirac measure at 1 of A. And that means it's 0 if 0 is contained in A, we get 1, and otherwise nothing. So let's recall Dirac of x was defined as the measure such that it's 1 if x is in A, 0 else. This is a proper probability measure, well defined. Okay. So this is our probability measure here, and what should be the random variable? Let's take as a random variable. Let's define x omega to be this type of random variable. Let's say it's 31 if omega is equal to 1, and it's -1 if omega is 0. Can you recognize what these numbers are? 31 and show me green light if you know why I put 31 and not 32. Okay, you haven't entered old Fennia building. That's the casino, Helsinki Casino. So if you go to Helsinki Casino, you play the roulette game. So this is a roulette outcome. So probability of roulette hitting the right number, that your lucky number is 1/37, and if you get your lucky number, then the roulette is paying you in the ratio 30:1. So then if you get your lucky number, you get 31 euros, and if you don't get so, you lose 1 euro. And probability of losing is 1 minus p is 36/37. So in case you want to go to casino with the machinery of measure theory and you want to calculate, okay, what's the expectation of x? So what's the expected value of one round of playing roulette in the casino of Helsinki? So we have all the definitions in place. How do we calculate this? By definition, this is the integral of x with respect to the measure p in this case. What next? Well, maybe now it's a good thing to notice that x happens to be a simple function of this form. X is actually a function of form A1 indicator A1 plus A2 indicator some big A2. If we plug in A1 is equal to 31 and A2 is equal to -1, big A1 is equal. When do we get 31? When omega gives us 1. So the set of good things is, in this case, it's 1, and the set of bad things is, in this case, 0. So with this example, now we use this notation, x is this type of simple function. We can write it as with these indicators this way. Then we remember that integrals are linear, so we use linearity for this simple function, and then we get a1 times the integral of indicator a1 with this p plus the similar thing for the other thing. Then what's the integral of indicator function? It's the measure of that set, so we get the probability of a, and then we get a2 plus the probability of a2. Yeah. Then what? What's the probability of a1? A1 is the event where we only get this, A1 contains 1 point only, that's 1. If we plug in to the measure definition, we know that probability of set A1 is equal to P. Yep. So probability of A1 is equal to P. What's the probability of event A2? A2 is the event which contains that 1.0. You plug in here, probability of A2. This gives you 1. This gives you nothing. So probability of A2 is equal to 1 minus P. So if you plug in the numbers, this value is 31 times 1/37. That's actually the probability of winning, the amount of winning, minus 1 times 36 over 37. And if you do the arithmetic, so that should be -5 over 37. If I recall right, that's the expected value, how much you lose when you play one round of roulette on average. Are there questions about this example that you might have in mind? Okay, so that's how kind of basic, very basic probability connects to the really, really big construction of Lebesgue integration.